The first law of thermodynamics on its own is not sufficient to establish the explicit dependence of the internal energy of a thermodynamic system on its state variables. If we want to derive such a functional relationship, then we need empirical data besides the theoretical considerations on the nature of the system. Now we will present an experiment on the free expansion of gases, which helps to determine such a relationship between the internal energy of an ideal gas and its state variables. The free expansion of air was first studied by Gay-Lussac in 1807, and Joule performed the improved version of his experiment in 1845. Here we can see the apparatus used by Joule. It consists of two identical gas containers, which are connected with a tube and placed into a vessel filled with water, serving as a calorimeter. The gas containers are denoted by the letters R and E in the figure. The tube is closed with the valve separating the two containers from each other. The container R is filled with air at a pressure of 20 atmosphere, whereas the container E is evacuated. Let V1 and P1 denote the volume of the identical containers and the initial pressure in the container R respectively. If we open the valve, then the gas will expand and fill the evacuated container. As a result, the expanding gas equalizes the pressure in the containers and reaches equilibrium. Then the volume V2 of the gas after its free expansion will be equal to 2 times its initial volume V1, while its pressure drops to 10 atmosphere. That is, the final pressure P2 of the gas will be the half of its initial pressure P1. When Joule performed the experiment, he carefully measured the change in the temperature of the water in the calorimeter. However, he was not able to detect any change of the water temperature, which indicated that the gas did not absorb any heat from the water. Therefore, the initial temperature T1 of the gas was equal to its final temperature T2 in contradiction with the expectation that the gas would cool off under expansion. We also note that the product of the pressure and the volume of the gas is the same before and after its expansion, that is the initial pressure P1 of the gas times its initial volume V1, is equal to the final pressure P2 of the gas times its final volume V2. The expanding air in the containers can be considered as a given amount of ideal gas with a thermodynamic state determined by its pressure, volume and temperature. The relationship between the state variables of the gas is given by the ideal gas law stating that the pressure P of n mole gas times its volume V is equal to n times the gas constant R times the absolute temperature T of the gas. Now we can apply the first law of thermodynamics stating that the difference between the internal energy U2 of the gas in its final state and its internal energy U1 in its initial state is equal to the heat Q exchanged between the gas and the calorimeter, plus the work W done on the gas. Since no heat exchange was measured and the external forces did not do work on the gas filled in the containers with fixed walls, the heat Q and the work W are zero. Therefore the first law states that the internal energy of the gas is the same in its initial and final states, that is U1 is equal to U2. In the experiment, Joule demonstrated that the temperature of the gas is the same before and after the free expansion, while it doubles its volume and halves its pressure. Since the internal energy U of the gas is the same in the initial and the final states of the experiment, it cannot depend on its pressure and volume. Only the product of the pressure and the volume is the same before and after the expansion, which would allow us to express the internal energy as a function of the pressure times the volume, and the temperature. However, this product is directly proportional to the temperature, as the ideal gas law shows. Then we can express the internal energy as a function of temperature, which neither depends on the pressure nor the volume. The conclusion drawn from the result of the experiment is the following. The internal energy of an ideal gas depends only on one state variable, which is the absolute temperature of the gas. In other words, the internal energy U of an ideal gas is a unique function of its absolute temperature T. Let us discuss the consequences of this important result for an ideal gas undergoing change in isochoric and isobaric processes. First we consider an isochoric process, where an infinitesimal amount of heat is transferred to a given amount of gas in a constant volume, and the infinitesimal change in the volume of the gas is zero. We have already seen that the differential form of the first law of thermodynamics states that the infinitesimal amount dQ of heat delivered to the gas is equal to the infinitesimal change du in the internal energy of the gas, minus the pressure P of the gas times the infinitesimal change dV of its volume. In an isochoric process this equation reduces to the equality of dQ and du. The specific heat capacity CV of an ideal gas measured in an isochoric process is defined by 1 over the mass m of the gas, times the derivative of the heat Q absorbed by the gas with respect to its absolute temperature T for a constant volume. By substituting the first law into this definition, we obtain the following differential equation. The derivative of the internal energy U of the gas with respect to its absolute temperature T is equal to the mass m of the gas, times its specific heat capacity CV measured in an isochoric process. Here both the internal energy and the specific heat capacity depend only on the temperature. If the explicit dependence of the specific heat capacity on the temperature is given, we can write the internal energy of the gas as a function of temperature by integrating the differential equation. According to the measurements, the specific heat capacity of gases in a constant volume is independent of their temperature, at least in a wide temperature range. Then we will assume that the specific heat capacity CV of an ideal gas measured in a constant volume is constant. By integrating the differential equation we obtain the following solution. The internal energy U of the gas is equal to the mass m of the gas, times its specific heat capacity CV for a constant volume, times its absolute temperature T, plus an integration constant U0. This integration constant is the zero-point energy of the gas, that is the internal energy of the gas at absolute zero temperature. In classical thermodynamics the zero-point energy can be chosen to be zero, since the first law and its applications involve only differences in energy, and U0 always cancels out. Then we can conclude that the internal energy U of an ideal gas with the given mass m at the absolute temperature T is equal to the mass m, times the specific heat capacity CV of the gas measured in isochoric processes, times the temperature T, that is the internal energy of an ideal gas is directly proportional to its absolute temperature. We can also deliver an infinitesimal amount of heat to an ideal gas in an isobaric process, that is for constant pressure, where the infinitesimal change dP in the gas pressure is zero. Now we can use the first law of thermodynamics expressed in the terms of enthalpy stating that the differential of the heat Q is equal to the differential of the enthalpy H of the gas, minus the volume V of the gas times the differential of its pressure P. Since we can drop the second term in the right-hand side for isobaric processes, we see that the infinitesimal heat dQ absorbed by the gas is equal to the differential of the enthalpy H of the gas. The specific heat capacity Cp of the gas measured in isobaric processes is defined by 1 over the mass m of the gas, times the derivative of the heat Q absorbed by the gas with respect to its absolute temperature T for a constant pressure. By substituting this result into the first law, we obtain a differential equation for the enthalpy of the gas. That is the derivative of the enthalpy H of the gas with respect to its absolute temperature T is equal to the mass m of the gas, times its specific heat capacity Cp measured in isobaric processes. Although the specific heat capacity of gases at constant pressure depends on the temperature of the gas, it can be considered constant for a wide range of temperature. Therefore the integration of the differential equation gives the solution for the enthalpy of the gas which is equal to the mass m, times the specific heat capacity Cp for a constant pressure, times the temperature T, plus an integration constant H0. This constant is the enthalpy of the gas at absolute zero, which can be set to zero. Then we can write that the enthalpy of an ideal gas with the mass m at the absolute temperature T is equal to the mass m, times its specific heat capacity Cp measured in isobaric processes, times the absolute temperature T, that is the enthalpy of an ideal gas is directly proportional to its absolute temperature. The functional relationships derived between the internal energy and the enthalpy of an ideal gas and its temperature are also known as the caloric equation of state for an ideal gas. The first caloric equation of state of an ideal gas for a given mass m at the absolute temperature T states that the internal energy U of the gas is equal to the mass m, times the specific heat capacity Cv of the gas for a constant volume, times the temperature T, which is equal to the heat capacity Cv of the given amount of gas for a constant volume, times the temperature T. In the second caloric equation of state, the enthalpy H of the gas is given by the mass m, times the specific heat capacity Cp of the gas for a constant pressure, times the temperature T, which is equal to the heat capacity Cp of the given amount of gas for a constant pressure, times the temperature T. If we divide these equations by the mass m of the gas then we can write them as follows. The specific internal energy u of an ideal gas is equal to its specific heat capacity Cv for a constant volume, times the absolute temperature T. The specific enthalpy h of an ideal gas is equal to its specific heat capacity Cp for a constant pressure, times the absolute temperature T. Here the specific internal energy u of a substance is simply defined as the ratio of its internal energy U to its mass m, which has the unit joule per kilogram. Similarly, the specific enthalpy h of a substance is simply defined as the ratio of its enthalpy H to its mass m with the unit of joule per kilogram. Since the enthalpy of a gas is defined by the sum of the internal energy and the product of the pressure of the gas and its volume, the product of the pressure and the volume is just the difference between the enthalpy and the internal energy. Then we can combine the caloric equations of state of an ideal gas by writing that the pressure P times the volume V given by the enthalpy H minus the internal energy U is equal to the mass M times the specific heat capacity Cp for a constant pressure times the absolute temperature T minus the mass M times the specific heat capacity Cv for a constant volume times the absolute temperature T. If we factor out the mass and the temperature in the right-hand side, then we obtain that P times V is equal to the M times the difference of Cp and Cv, times T. Now we can apply the ideal gas law for a given amount of gas, which states that the pressure P of the gas times its volume V is equal to the amount N of the substance, times the gas constant R, times its absolute temperature T. The right-hand side can also be written as the mass M of the gas, times its specific gas constant Rs, times its absolute temperature T. The specific gas constant Rs of the gas is given by the ratio of the universal gas constant R to the molar mass M sub M of the gas, which is equal to the amount N of substance times the gas constant, divided by the mass M of the substance. Then we can write that the mass M times the difference between Cp and Cv, times the temperature T is equal to the mass M, times the specific gas constant Rs, times the temperature T. This expression reduces to a relation stating that the difference of Cp and Cv is equal to Rs, which is Meyer's relation. We have already derived this relation in another form, which we can see if we express the mass M times the difference between Cp and Cv times the temperature T, as the amount N of the substance, times the gas constant R, times the temperature T. This gives an expression stating that the difference of the heat capacities Cp and Cv of the substance is equal to N times R. If we divide this result by the amount N of the substance, then we regain Meyer's relation from the caloric equation of state for an ideal gas and the ideal gas law. As a result, this relation can be written in two alternative forms. The first one states that the difference between the specific heat capacity Cp for a constant pressure, and the specific heat capacity Cv for a constant volume is equal to the specific gas constant Rs of the gas. In its second form, Meyer's relation tells us that the difference between the molar heat capacity C sub Pm for a constant pressure, and the molar heat capacity C sub Vm for a constant volume is equal to the universal gas constant R. We can also determine the internal energy of an arbitrary homogeneous and isotropic body as a function of its thermodynamic parameters. The state variables of such bodies are the pressure exerted on the body by an external force, the volume of the body and its temperature. The equation of state for the body provides a functional relation between these state variables. As in the case of an ideal gas, one of the state variables can be expressed in the terms of the other two variables by solving the equation of state for it. Then we are able to reduce the number of independent variables describing the thermodynamic state of the body. We can write the pressure as a function of the volume and the temperature of the body. We can express its volume in the terms of the pressure exerted on it and its temperature, or we can give the temperature of the body as a function of the pressure and its volume. As a result, the internal energy of the body, which is a state function, depends on only two independent state variables. In other words, the internal energy U can be expressed as a unique function of the volume V and the temperature T, the pressure P and the temperature T, or the pressure P and the volume V. For an isochoric process, where the heat absorbed by the body increases its internal energy, that is dQ is equal to du, we could write the specific heat capacity Cv of the substance as the mass M of the body, times the derivative of the internal energy U of the body with respect to its absolute temperature T for a constant volume. Similarly, for an isobaric process, where the heat absorbed by the body increases its enthalpy, that is dQ is equal to dH, we could write the specific heat capacity Cp of the substance as the mass M of the body, times the derivative of the enthalpy H of the body with respect to its absolute temperature T for a constant pressure. Since an infinitesimal change in the enthalpy H at a constant pressure is equal to the infinitesimal amount of heat Q, that can be written as the mass M of the body, times the specific heat capacity Cp of the body measured at constant pressure, times the infinitesimal change in the absolute temperature T of the body. We can also apply the definition of enthalpy to derive its infinitesimal change in isobaric processes, and write it as the differential of the internal energy U, plus the pressure P times the differential of the volume V. If we combine these two equations, then we obtain an expression stating that the partial derivative of the internal energy U of the body with respect to its absolute temperature T for a constant pressure is equal to the mass of the body, times its specific heat capacity Cp for constant pressure, minus the pressure P times the derivative of the volume V of the body with respect to the absolute temperature T for a constant pressure. At the same time, we can also differentiate the internal energy U as a function of the volume V and the absolute temperature T with respect to the temperature for a constant pressure. Then its partial derivative can be written as the partial derivative of the internal energy U with respect to the volume V for a constant temperature, times the partial derivative of the volume V with respect to the absolute temperature T for a constant pressure, plus the partial derivative of the internal energy U with respect to the absolute temperature T for a constant pressure. In the first term, we use the chain rule of the derivative of the composition of the functions U and V. Since the left-hand side of these equations are the same, we can combine them into one expression. As a result, we can state that the mass m times the specific heat capacity Cp, minus the pressure P times the derivative of the volume V with respect to the absolute temperature T for a constant pressure, is equal to the partial derivative of the internal energy U with respect to the volume V for a constant temperature, times the partial derivative of the volume V with respect to the absolute temperature T for a constant pressure, plus the mass m times the heat capacity Cv. Here we substituted the expression of the heat capacity Cv obtained for a constant volume into the last term in the right-hand side of the equation. If we regroup the terms and divide the result by the mass m, we obtain a relation between the specific heat capacities of a homogeneous isotropic body, which is the following. The difference between the specific heat capacity Cp of the body for a constant pressure and its specific heat capacity Cv for a constant volume is equal to 1 over the mass m of the body, times the sum of the partial derivative of the internal energy U of the body with respect to its volume V for a constant temperature and the pressure P, times the partial derivative of the volume V with respect to the absolute temperature T of the body for a constant pressure. This general relation links such properties of the body with each other that can be measured in different thermodynamic processes. In an isothermal process that is at constant temperature, there is a unique relation between the internal energy of the body and its volume. In a general case, any change in its volume also causes some change in its internal energy, which can be described by the partial derivative of the internal energy U with respect to the volume V at a constant temperature. In an isobaric process, we can measure the specific heat capacity Cp of the body as a function of temperature, and determine the change in its volume as a function of its temperature. The partial derivative of the volume V with respect to the absolute temperature T for a constant pressure gives a quantitative description of this function. In an isochoric process, we can measure the specific heat capacity Cv of the body as a function of temperature. Since this relation is a general description of the thermodynamic properties of a homogeneous and isotropic substance, we can consider a given amount of ideal gas as its special case. The ideal gas law states that the pressure P of the gas times its volume V is equal to its mass m, times its specific gas constant Rs, times its absolute temperature T. Then the volume of the gas is just directly proportional to its absolute temperature for a constant pressure, where the proportionality constant is equal to the mass m times the specific gas constant Rs, divided by the pressure P. The internal energy U of an ideal gas is given by the mass m of the gas, times its specific heat capacity Cv for a constant volume, times its absolute temperature T. This equation shows that the internal energy of the gas does not depend on its volume. If we use these results to determine the partial derivatives in the relation, we obtain the following. The partial derivative of the internal energy U of an ideal gas with respect to its volume V for a constant volume vanishes, whereas the partial derivative of the volume V of the gas with respect to its absolute temperature T for a constant pressure is equal to the proportionality factor m times Rs divided by P. The specific gas constant Rs is equal to the universal gas constant R divided by the molar mass m sub m of the gas. By substituting these expressions into the relation, we obtain Meyer's relation as expected. That is the difference between the specific heat capacity Cp of the body for a constant pressure and its specific heat capacity Cv for a constant volume is equal to the universal gas constant R divided by the molar mass m sub m of the gas. We can interpret the general relation between the specific heat capacity Cp and Cv as follows. If the equation of state of the body is given, that is its pressure P is a function of its volume V and its absolute temperature T is known, then the volume V can also be expressed as the function of the pressure P and the absolute temperature T. It allows us to determine the partial derivative of the volume V with respect to the temperature T for isobaric processes. Furthermore, we need some data obtained from measurements to evaluate this relation. The specific heat capacity Cp and Cv as functions of the volume V and the temperature T are measured for different types of materials in experiments. Such data can be used for the homogeneous and isotropic body made of a given material. For isochoric processes, the heat capacity CV of the body determines the partial derivative of its internal energy U with respect to the absolute temperature T. The partial derivative of the internal energy U with respect to the volume V for a constant temperature can also be computed by substituting the specific heat capacities and the partial derivative of the volume with respect to the temperature for a constant pressure into the relation. Now we have all the information to determine the internal energy of the body. The total differential of the internal energy U as a function of the volume V and the absolute temperature T can be written as the partial derivative of the internal energy with respect to the volume for a constant temperature times the differential of the volume, plus the partial derivative of the internal energy with respect to the temperature for a constant volume times the differential of the temperature. Since we have determined the partial derivatives in this expression, the differential is also determined. By integrating this expression, we obtain the internal energy of the body as a function of its volume and its absolute temperature.